In this lesson, we are going to review your exponent rules for like bases. So here's a vocabulary reminder. In this expression, 4 is the base, 3 is the exponent, and that exponent means that 4 is a factor 3 times. So if you would evaluate this, it would evaluate to 64. This can also be read as 4 cubed or 4 to the third power. So this chart has all the exponent rules I expect you to know. You have learned these in your Algebra 1 course, so this is more of a review where I don't necessarily go through where every rule comes from, but I'll provide you with a simple example. For more complicated examples, you're going to proceed to the next video. So this first one, notice that the bases are the same. This is equivalent to keep the base, you always keep the base, and you're going to add the exponents. A simple example of this would be if you had x to the third power times x to the fifth power. Well, that's equivalent to x, keep the base, and add your exponents, x to the eighth power. In the next one, this is known as power to a power, a to the nth power. This is equivalent to keep your base, and this time you multiply your exponent. A simple example would be x squared raised to the eighth power. This is a power to a power. You keep your base and you multiply the 2 times 8 to get 16. The next rule is very similar to your previous one, but notice this time that the exponent is on the outside. So this means you are applying the exponent to both factors inside. So in other words, you're distributing that exponent. This becomes a to the nth times b to the nth power. A simple example would be if I had xy to the fourth power. This gets distributed to both powers, or both factors inside, to become x to the fourth, y to the fourth power. In the next rule, the bases are held by division. What you do here is you keep your base and you subtract the top exponent minus the bottom exponent. So if I had x to the seventh divided by x to the fourth, the bases are the same. This becomes x to the 7 minus 4, or x cubed. The next rule, in a sense, combines our previous two rules. What you're going to do here is you have a quotient with a power on the outside. So this outer exponent needs to be distributed to each factor in the numerator and each in the denominator. This would become a to the mth power divided by b to the mth power. Now, if those bases were like, you could then subtract the exponents. So a simple example here would be if we had x over y, so I have a quotient raised to the fifth power. This would become, well, distribute both to the numerator and denominator, x to the fifth over y to the fifth. And those are not like bases, so I couldn't go any further. Now, any non-zero power to the 0 power, what does that become? I'm hoping you remember that that is equal to 1. And I can give you an explanation for that. Even though I said you should have learned this in a previous class, an easy way to think of it would be if you had 5 to the third divided by 5 to the third. Well, if we used our division rule, the rule is keep your base and subtract your exponents, that would be 5 to the 0. Well, isn't any value divided by itself in mathematics equal to 1? So our conclusion is 5 to the 0 has to be 1, right? So any non-zero power raised to the 0 power. So if I had something like this, no matter how complicated it is on the inside, it's raised to the 0, it's equal to 1. Now, in Algebra 1, for negative exponents, you learn that a negative exponent does not make anything negative. Instead, it causes it to become a fraction. This is equivalent to 1 over a to the positive nth power. I always said, think of this as a fraction now, and what it does is it flips the side it's on and your exponent switches to positive. So if I have x to the negative third power, that is equal to 1 over x to the positive third power. And our final rule, kind of combining two previous ones, you could distribute this outer exponent, or you could recognize that a negative exponent causes your base to do a backflip. So this becomes b over a to the nth power, like this, which is then b to the nth over a to the nth. A simple example here would be if you had x over y raised to the negative second power, well, does a backflip, exponent becomes positive, and now you can distribute this outer exponent, so it's y squared over x squared. So these are all the exponent rules that you need to be able to quickly apply. I'm going to show you a quick memory trick to help you remember a lot of them. The memory trick has to do with the order of operations, which you know as PEMDAS. So you would do parentheses, then exponents. You were taught to multiply or divide from left to right, so I'll put those next to each other, and add or subtract from left to right. So what does this have to do with exponent rules? So what you're going to do is, if the bases are the same, you're always going to keep the base. And then you're going to apply the next weakest operation from the hierarchy to the exponent. So what on earth do I mean by that? Let me show you. So if I have y to the 4th times y to the 7th, okay, and you forget what to do. So you look at your rule, your operation, and you see it's held by multiplication. You go over here to multiplication, and what do I mean by the next weakest? What's immediately below it? There's a for addition. So that's telling me I keep my base and I add my exponents. Okay. If I have y to the 4th to the 7th, what operation is connecting this? Well, this would be an exponent raised to another exponent. So I'm at e. So what do? I keep the base, and then I apply what's immediately below it. I'm going to multiply my exponents together to get y to the 28th power. So if it's held by division, y to the 15th over y to the 3rd. Okay, held by division, here's division. What do I do to the exponents? Immediately what's below it, I'm going to subtract to get y to the 12th power. If you're at y to the 5th plus y to the 4th, well, this is at addition. What's immediately below it? Nothing. You don't do anything. In other words, there is no exponent rule for addition. You have to use your combining like terms rule. There are no like terms, so that is simplified. So I hope this memory trick helps you remember all of your rules. It works for me rather than memorizing that entire list. In the next video, we will perform more complicated examples, so please take a piece of paper and practice those with me.